So far, I have explained that the important mechanical properties include rigidity, strength, hardness, and ductility. We have already discussed rigidity and strength. Next is about hardness. Rigidity indicates the resistance against deformation in the elastic range of a material. Strength indicates the amount of force that a material withstands and its resistance to failure. These values are available in catalog. On the other hand, hardness, introduced here, evaluates the resistance of a material against the force applied at the local point on material surface. How we may measure the hardness. There are several methodologies for hardness measurement. These can be broadly divided into two types. The first is to forcing an object on the surface of a material to quantify the size of the indentation. The second is dropping an object on the surface of a material to measure the height of bouncing. Now, I am introducing a few types of hardness measurement that force a test piece on the surface of a material to quantify the size of the indentation. Brinell hardness is measured by dropping a steel ball on the material to measure the diameter of the indentation. Due to the larger area of the indentation, this measurement is not suitable for sheets, small objects, and hard objects. The symbol for Brinell hardness is HB double. Vickers hardness is a method in which a square pyramid is pressed against the material to determine the length of the diagonal of its indentation. Since the area of the indentation is small, this measurement is suitable for thin sheets, small objects, and hard objects. The symbol for Vickers hardness is HV. Rockwell hardness measures the depth of the indentation when the cone is pressed against the material. This measurement is suitable for the products after heat treatment. The symbol for Rockwell hardness is HRC. Shore hardness is a little different from previous hardness tests. The test specimen is dropped and its height of bouncing is measured. The advantage is that this measurement does not cause noticeable damage on the test piece. The symbol for shore hardness is HS. With respect to these measurement methodologies, you should notice that hardness is very closely related to the yield point in the stress-strain diagram. Roughly speaking, a harder material has a higher yield point. A material of a higher yield point tends to have a higher tensile strength. So, the yield point and tensile strength can be approximated from the hardness. As one rule, it may be useful to remember that tensile strength is 3 times the Rockwell hardness, as shown in the following equation. However, since this value is an empirical guide, further study, such as endurance testing, is required to actually guarantee the product quality. Now, let's consider why we need hardness while rigidity, yield point, and strength are given in material catalogs. This is because these properties in catalogs are given under the assumption that the material is homogeneous. At the phase of initial material selection in a machine design, you may refer the properties in catalogs to select materials. However, there is no guarantee that the equivalent properties remain after various manufacturing processes. In practice, materials undergo various processes such as heat treatment, machining, forging, and others after they are obtained. The process of machining and forging may cause work hardening. Heat treatment makes only the material surface harder. Under these conditions, we cannot guarantee the product quality based on properties given by catalogs. So, in order to guarantee the quality of the product, the hardness of the weakest region of a product may be tested with respect to the performance of existing similar products. The hardness test can be carried out on the actual products without destroying them. Verification of the effect of quenching and tempering may be an example.